So Emmanuel Bourgeois from University Gustave Eiffel. I can introduce yourself. So Emmanuel is a senior researcher at University Gustave Eiffel. He has been working in the field of numerical modeling in geotechnical engineering for more than 20 years, first in LCPC and then after in IFSTAR, and is involved in the development and the maintenance of the finite element code César. And so I let you start your presentation, and you have 20 minutes.
Thank you, Sebastian. I'm very honored to be here today, and I would like first to thank the organizers for giving me the opportunity to say a few words about the use of the finite element method applied to embedded walls. First, a short introduction, then I will recall what is taken in the simulation and what is not, and this will make us make it possible to discuss current level of confidence and accuracy. Well, what the method is good at and what it is not so good at. I will then present a few more complex cases and say a few words of perspective. So today, the finite element method is very widely used for embedded walls, but of course, it's not the only approach. There are analytical models or other numerical methods, for instance, the subgrade reaction modules method. And arguably, the finite element method is maybe not the simplest one to use. Basically, for embedded walls, the method is used for elastoplastic simulations. I didn't even mention that it's in statics. And for service limit states, basically, even if now there is a trend to extend the approach to stability analysis, computation of safety factors, but this is a rather recent evolution due to the evolution of design rules, actually. In most cases, we remain in the framework of plane strain analysis, which means that the computations are reasonably fast, and the risks of error are rather well identified. So the finite element method remains relatively easy to use, but it's more complex than other approaches, you can say. The idea is to represent the real problem by a set of partial differential equations and to solve them numerically. So you have to make choices to do so. You have to build a numerical model, and you have, for instance, to choose between plane strain and 3D. And as I mentioned before, mainly we use plane strain. You have to make other choices that are more numerical ones between types of finite elements. For the wall, for instance, you can choose between beam elements or solid elements. And also you have to choose a constitutive model. And since I've mentioned we are dealing with elastoplasticity, we have to pay special attention to the type of model. And the results we obtain in the case of service state computations is the displacements of the wall and also in the ground surrounding the wall, and also forces and moments in the wall and forces in the supports, the props or anchors. In the case of stability analysis, we get safety factors for each intermediate construction step. Okay, but we must remain aware of the fact that our numerical model is a simplification of the real problem. For instance, here you have on the left a picture of the station of the Grand Paris Express in Le Blanc-Ménil, not far from my home. It's the future line 16. And the numerical counterpart, with my favorite finite element code, is on the right. And obviously, there is simplifications. I have just circled in red one example. The connection between the prop and the wall is, of course, very simplified on the right, because it's just a point connection with the continuity of the displacements, and that's all. That's a little simple, and on the picture, of course, there are all sorts of activities around the excavations that are not taken into account in the model. And also in the angle of the excavation, you have an angle prop, which is of course not present in the plane strain analysis. So we can wonder if our models are not a little too simple in some cases. So this is maybe a reason to list what is in the simulations. We have 5 key elements. You need to have a numerical procedure for the modeling of the excavation process. And this is not really in the initial framework of the finite element. You have to program to introduce a specific procedure, which can be more or less clever and more or less accurate. You also have to pay special attention to the constitutive model, and we know since the work by Schweiger in 20 years ago, they organized a prediction exercise on an actual site in Berlin, and they compared the relevance of constitutive models by making comparison between predictions and measurements on the real wall. And well, we can make all sorts of comments on the comparison, but one of the very clear conclusions is that you need at least a hardening model to have a reasonable representation of the wall behavior. You also have to introduce a specific model for the ground wall interface, even if you keep it simple. Well, there is a large difference between results obtained with and without a specific model for the interface. Then you have to take into account and to model numerically, to introduce in the computation the role of the support system, including pretensioning and of anchors or props. And in the last place, in case you have water table variations, which happens often, you have to introduce a specific model for that too. And it's relatively difficult to check the results because we don't have appropriate data to be very sure of what of the results we obtain. Okay, and by contrast, there are some things that are more or less ignored in the models. The details, for instance, the wall construction is generally ignored, which may be of consequence in some cases. Local 3D effects are by nature ignored, and some other details are not really captured. For instance, the actual spacing and the position of the props is necessarily simplified. Some key steps of the construction, like the cutting of the wall head, are generally not discussed. And in a more general way, the details of the actual sequence of the works, possible temporary loads, are not really described. Thermal effects are rarely discussed, and they may induce additional loads in the props. Effects such as creep in the wall are not discussed, well, in most cases. And there are also questions that are not easier for embedded walls than in a general situation. For instance, the role of the unstatuated behavior of soils, or the undrained strength, which is an open question in many cases. So we can nevertheless try to assess the current level of accuracy and confidence we have. We have comparisons between simulations and experimental results. So we know that the results are rather satisfactory for the horizontal displacements of the wall and for the forces and moments in the wall and in the supports. We also know that, well, at least I'm convinced, that the finite element method takes into account arching effects in the ground rather better than other methods, and especially in some cases where arching can be more spectacular, more important. Okay. Nevertheless, well, as I mentioned before, there are some details that are relatively grossly represented or purely ignored. And also, I would like to mention that we have less confidence regarding the settlements behind the walls because we lack actually documented case studies. It's difficult to get measurements because the site is used for many other things than just placing targets. So we lack appropriate data to be sure that the settlements are properly predicted by the models. I would like to make a small comment about the evolution of the size of the numerical models. I borrowed the first picture to Bruno Simon. It's a little more than 20 years ago, and well, roughly the number of degrees of freedom, is around 1,000, maybe 2,000. And I have given a few more recent examples, but as you can see, as long as we remain in the plane strain assumption, well, there is no reason to go beyond 40 or 50,000 degrees of freedom, which means that we feel at ease. The picture on the right and the bottom showed that there was an increase in the size of the problems up to 2000, 2010, but now we don't feel it necessary to increase the size of our models. We feel comfortable and the simulations run rather rapidly. And this is in contrast with the case of tunnels, because here, in general, it is necessary to use 3D models, and there is no really the trend has not stopped, and the size of the models still increase. So we are around currently 1 million or several million of degrees of freedom, which means that we use all the available computation power, and if it keeps increasing, very probably our models will also keep increasing. Yet there are some situations in which we use 3D models. This one is 20 years ago. The mesh is rather coarse. We are around 50,000 degrees of freedom. And what makes it necessary to use 3D is that the road between two walls, the depth of the road increases along the wall, and also there is a slab that blocks the displacement of the wall head. So it was necessary to use 3D. I didn't show the comparison with the measurements, but it was rather good. More recently, this is taken from the PhD by Radhija Nejar. It's around 1 million degrees of freedom, and it's a station of the Grand Paris Express again. And here, the interest of the 3D approach is that we can discuss the influence of the angle probe, for instance. And this is an attempt to compare to evaluate the error made if we remain in plane strain. So here, 2D simulations tend to overestimate the force in the angle probe. And a more recent one, imported from London. Here, I don't know if it's still an embedded wall, but there is a complex geometry of the structure. And also there are, as you can see, neighboring loads that are difficult to introduce, of course, in a plane strain analysis. So in this case, they had to use a model. I don't know the number of the size of the model, but we are certainly above 1 million degrees of freedom. Okay, so at the conclusion, the plane strain simulations are used routinely for embedded walls. The method is robust and reliable, and there is a certain consensus about how the computation must be carried out. And I would not say the same for tunnels, for instance, whereas there is still a wide discrepancy between the approaches. And as I pointed out, there are still a few specific questions that remain to be studied more in detail. The approach could be validated because we had site data. So this is a very important thing. Finite element models, and the same holds for the other techniques of computations, such as the artificial neural networks, deep learning, reduced basis, whatever. We need experimental data, good quality experimental data if possible, to validate and to calibrate the model to be sure of what results give. So this is, again, why we are less confident about the settlements behind the walls, because it's difficult to measure. And there is also more or less the same thing about the distribution of pore pressure around the excavations during the works. Okay, so a few words of perspectives. Well, first of all, is there a need for more complex constitutive models? I'm interested in the question, so I would have liked to answer yes. But at the moment, people seem to be satisfied with typically the hardening soil model, because more advanced models would imply more difficulties in parameter identification. The discussion is not closed, because if we want to improve the prediction of the settlements, provided that we measure it, probably we will have to start a new cycle of reflection about the constitutive models. Second question, what can 3D models bring? Well, we can improve the understanding of some phases of the construction, especially the construction of the wall. And we could, of course, better simulate the actual construction phases and some details. Third question is, how can we make our tools evolve? Well, there's certainly room to improve the ergonomy, to make computations easier to perform, and to make results easier to check also. And maybe there's another evolution that can be anticipated to go towards design tools rather than computation tools, because at the moment, we have the feeling that engineers spend much time tuning the model, and maybe there's space to improve, to have automated model correction, for instance. It would save time, provided that it's done with appropriate methods, I would say. And in the last place, we can wonder if finite element simulations can be combined or completed with other approaches. Well, it's already the case. There is a clear trend nowadays to use the finite element to constitute the data that are required to train artificial intelligence to say things shortly, artificial neural networks or that type of methods. Voilà, I thank you for your attention.